Okay, this is chapter 15 for Physics 105. This is about traveling waves in sound. Now, caution, we're going to use a lot of this in Physics 106. So if you're going to take Physics 106 in the fall, pay attention. Okay, here's the objectives. Understand how waves travel through a medium. Understand the mathematical description of sinusoidal waves, sines and cosines. Apply the wave model generally and understand how it applies to the specific cases of waves on strings, sound waves, and light waves. Apply energy and power concepts to waves. Use the decibel scale for sound intensity and understand the Doppler effect. This is used in medicine. I mean, a lot of it, well, you'll see. You'll see. Okay. Why do we care about waves? Sound is a wave. Light is a wave. When we do quantum mechanics in Physics 106, quantum mechanics describes how nature works at a really small scale, like atoms and that. It's waves. In the hospitals, waves, ultrasound, right? Doppler measurement device to measure how fast the blood is traveling. There's all sorts of applications for waves. So it's really, really important. Okay, the first thing we want to do is we want to talk about particles versus waves. Or I should say particles and waves. Now, up to this point in physics, we've pretty much assumed everything is a particle, right? For example, like if you're going to draw a force diagram, this could be a car. The car could be the object. You just draw it like it's a particle, right? We've just used the particle model. And what's the particle model? Well, a particle, we say it's localized. It's at one specific location. Right? A particle has mass. A car has mass. This thing has mass. But let's talk about a wave. Here's a wave. Can you say a wave is at one specific point? No, a wave is spread out. Can you say a wave has mass? I mean, what does that mean? A wave has mass? I mean, the water has mass, but a wave, it's just like a disturbance, right? You don't talk about a wave having mass. How about the ability to pass through each other? So look. Here you have two baseball pitching machines. So the machine shoots out a baseball. So let's say that the machines shot out baseballs at the same time at the same speed. Well, they would collide, right? And they wouldn't go through each other. That'd be kind of weird, right? They just bounce off each other. So the balls collide and bounce apart. Two particles cannot occupy the same point of space at the same time. No kidding. I mean, right? The hand doesn't go through the wall. All right. On the other hand, let's talk about waves. Here's a speaker. Here's a speaker. What do the waves do? They just pass right through each other. Can you imagine going to a concert? What would it sound like if the waves didn't pass through each other, if they were somehow reflecting off each other? Oh my gosh, it'd be a mess. Okay, so unlike particles, waves pass directly through each other. All right, so what I want you to understand is particles and waves are completely different. Now, what does this mean? It means that I'm lying. All right? So as far as classical physics is concerned, waves and particles are completely different. But when we study quantum physics, which is required to learn about atoms and things like that, in Physics 106, we're going to see that particles and waves are not completely different. But for Physics 105, they are completely different. All right, so we want to basically look at two types of waves, longitudinal and transverse. So if I had a piece of rope attached to a doorknob, and I go like that, that's called a transverse wave. It would look like this, right? And you see the disturbance moving along. On the other hand, if I had a spring, like a slinky, and I just would go like this. You know, you'd see the disturbance go like this. So let me show you a video.
Longitudinal wave, the disturbance that makes up the wave, is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
All right, so basically, with a transverse wave, like with a rope, you know, I would have to go like this, right? And so the wave is going in this direction, but I'm going transverse to it. With a longitudinal wave, I go like that. And so I'm going in the same direction as that the disturbance is moving. Be nice. All right. Okay, so this is a nice picture, right? So this is a transverse wave. So the wave, the disturbance, moves this way, but yet what did I do to get it going? I had to go up and down, right? So transverse means perpendicular. So the disturbance is moving this way, but I had to go like that. So perpendicular, right? This is perpendicular to that. Sinusoidal, right? So the wave is going in this direction, the displacement going in that direction. But what did I do? I went like this, right? So parallel or anti-parallel, okay? So those are there's other forms, but those are the major types of waves that we're going to talk about. Transverse and longitudinal. Okay, now here's the question. So let's say you are holding the rope right here, and I have the rope here, and I'm wiggling up and down. So what is being transported between me and you? I mean, is a piece of the rope going between me and you? Well, of course not, right? Certainly not, okay? Let's pretend that I have a piece of, let's say I have a can of spray paint, and I spray this red or something, okay? Now, when I make a transverse wave, what would happen to this rope that I sprayed paint? It would just go like this, right? What if I sprayed the spring? What would it go? What would it do? Okay? All right? So what is moving between me and you? It's the disturbance, or you can say it's the wave pulse, right? It's just the disturbance. It's not a piece of the rope. It's just the disturbance, okay, the wave pulse. Now, let's say I got really excited and I started shaking like crazy. What would you feel? What would you feel over there? You'd feel the vibrations, right? Well, work is required to produce the vibrations. And so what does a wave transport? Energy and also momentum, right? Okay, so and here's a quick example of waves transporting energy. Have you ever had a sunburn? Well, if you've had a sunburn, where'd the energy come to burn your to burn your skin? The sun, right? So, think about it. That energy traveled all the way from the sun to your body, 93 million miles. It's incredible, right? So waves transport energy and momentum. So here's kind of like a nice definition of a wave. A wave is a self-propagating disturbance that travels through an elastic medium, transports energy and momentum. Let's discuss it. What do you mean it's self-propagating? Well, it is. Think about it. Think of the rope again. Okay, I have to start it, right? So I have to give it one flick, right? But then what does it do? It just keeps on going, right? It just keeps going, you know? And what is this elastic medium? Well, you know, if you had a rope that was like infinitely tight, you know, it really wouldn't, you couldn't disturb it, right? And so the medium has to move a little bit, okay? So I put quotes around it, right? So the medium. By the way, what do I mean by medium? Okay, what's the medium for a rope wave? Rope. What's the medium for a water wave? Water. What's the medium for an earthquake wave? Earth. You know, and so forth and so on, okay? What's the medium for sound wave? Air. Okay, and again, it transports energy and momentum. All right. Let's see. Oh, this is tough, believe it or not. A wave on a string is traveling to the right. So we see this wave pulse moving to the right. At this instant, the motion of the piece of string marked with a dot. So what we're saying is we took a can of spray paint and we sprayed, you know, the rope right there. So at this instant, the motion of the piece of string marked with a dot is what? So pause your video and think about it. Okay, now remember it's a transverse wave. So all it can do is go up and down, right? But this wave is moving to the right. Agree? So what's going to happen to this thing? So this piece here is moving this way. So that means that this thing is going to go up. Okay, it's going to go up. So up. All right, it's going to go up. Okay, now we want to talk about wave speeds. Oh my goodness. All right. So we'll use this one a lot in this chapter. We use this a lot. Well, we use this a lot in this chapter and especially in Physics 106. We're not going to use this hardly ever. Okay, so if you have a string or a thin wire and you're just, you know, doing this to it, right? It's attached over there and you're just doing this. The speed of the pulse, right, the wave pulse, equals square root of the tension over this mu. This is called the mass density, mu. Mass density is just mass of the rope or string, sorry, divided by the length. Okay? So the string or thin wire. Now, this is kind of important. If you know, like, again, let's say you connect a string, doorknob over there, doorknob over there. And then in order to get a wave going, you just give it a flick or something like that, you know? And so, you know, when you set it up, you have a certain tension, right? How tight it is. You have a tension, and the string, you know, you buy a string with whatever mass per length. Now that means that's the only things that the speed depends on. So in other words, if I gave it a little flick or a big flick, doesn't matter. The speed doesn't depend on the amplitude, how much I flick it. It only depends on the tension and the mass per length. Okay? Okay, so that's that one. Sound, you know, it depends on the temperature of the air. That's all I really care about. And this is the strange one, and you'll understand that when we do Physics 106. The speed of light, so we usually say the speed of light is c. So whenever you see lowercase c, it means speed of light. 3 times 10 to the 8th meters per second. It's fast. Now, the strange thing about this is everybody measures this to be the same. So this is that's weird. Here's why it's weird. Let's say I have a rocket. And the rocket is traveling at 99% of the speed of light. Then the rocket turns on a beam, a headlight, right, or something like that. Now, of course, the speed of the light is the speed of light, right? Okay, now, let's say we're on the Earth watching all this. Okay? What would we measure the speed of light from the headlight? Now, Isaac Newton would have said, well, the speed of light is the speed of light from the headlight plus the speed of the rocket. That sort of makes sense, right? It's wrong. Everybody measures the speed of light to be the speed of light. Weird, but it's true. Okay, so this is what I'm saying. I mean, here's another picture of what I'm saying. So here we have a train moving to the right. We have a runner moving to the right. The runner is carrying a flashlight. So the runner is going to measure the speed of light from his flashlight as the speed of light. I mean, no kidding, right? But what's interesting is the guy on the earth is also going to measure the speed of light. I don't care how fast the train is going. I don't care how fast the runner is going. Everybody measures the speed of light to be the speed of light. Now that should make no sense at all. And we'll resolve that when we talk about physics, in Physics 106 when we talk about special relativity. All right, here's a question for you. And let me give you a hint. So for a string or for a thin wire, the speed is the tension divided by the mass per unit length, right? Mu is the mass per length. All right, so these two wave pulses travel along the same stretched string, one after the other. One has a large amplitude, one has a small amplitude, but it's the same string, right? It has the same mass per unit length. We're assuming that the tensions are the same, everything is the same, but one has a large amplitude and one has a small amplitude. What is true about the speed? So pause your video and answer it. Okay, well, once again, just look at the formula. Does it depend on the amplitude? No. It only depends on the characteristics of the string and how tightly the thing is held. Amplitude is irrelevant, which is weird, but it's true. Okay, what we want to do now is we want to visualize one-dimensional waves. And we can do that with two types of graphs or two plots, snapshot and history. And these are great names. You know, when you take a photograph of something, you call it a snapshot, right? And so what you're doing is you're seeing what something looked like at one particular time. On the other hand, what's history? You know, history is over lots of time, right? So that's what it is. Anyway, you'll see. Okay, here's the thing. So here's a spring. And so we start here, all right? So time goes this way, right? So this is like t equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever, you know? So time goes this way. And here's a piece of, I don't know, they sprayed this, or whatever, this piece of spring, okay? And so here we are, time equals 0, and we give the spring a flick, okay? So you see, there's the flick, you know, small. And then here it is. So you see the wave pulse is moving to the left, agree? And look at it, this is not touched at all. Then finally, the pulse gets here and it starts moving it. Then the pulse goes here, pulse goes there, pulse goes there. All right? Okay, so why did I show you that? Well, the only reason I showed you that is because, okay, now this is called the displacement, all right? When the wave is displaced, right? Here it's not displaced, here it's displaced. So look at that slide. The displacement depends on x, right? It depends on where, because here it's here, there, right? So the displacement depends on x, where you are on the wave, but it also depends on time. So the displacement depends on two variables. Displacement depends on x and t. And we've never had anything before that had two variables like that. So, wow, all right? So since we don't have a movie, sorry, we're going to use two graphs to learn about this. Okay, first thing, so we're trying to visualize these one-dimensional waves. Okay, so again, now let's just talk about the snapshot. So just imagine, you know, that I stand here and I flick the rope, and you just stand there and take a picture at one particular time. So you're seeing, you know, what the wave looked like. The whole, you're looking at the entire rope, right? You're seeing here where there's nothing, then you see here, maybe there's a displacement, maybe there's nothing there, whatever. But you're just looking at it at one particular time. You're seeing the entire rope, the x dependence, right? Okay, so each one of these is a snapshot, right? I mean, here, you know, we took a picture of the wave at this particular time, then we took a picture of the entire wave at this particular time, and so forth and so on. So every one of these is what we call a snapshot plot, all right? Okay? It's just a picture of the entire wave at one particular time. Okay, now these are a little, well, okay. So here we have a wave. Okay, so here's the wave pulse, right, or the disturbance, okay, at time equals t1. And then we're going to say it's moving to the right, I agree? And so it's moving this way, right? So this piece of the wave will have moved delta x, right? And delta x is v delta t. So in other words, from t1 to t2, this pulse moves to the right, right? It doesn't, you know, the wave moves without changing shape because the pulse is moving to the right. So after one, so from t1 to t2, it moves delta x. So this point now is over here. And then at t3, this point now moves over there, right? So, okay. So the wave moves without changing shape. The wave moves forward, delta x equals v delta t, during the time interval delta t. So, okay, so big, you know, so there it is. Then it goes there, then it goes there, then it'll be there, and so forth. So you just imagine that this triangle is just moving to the right. Okay, so this is a snapshot, right? That's what it looks like at time 1. This is a snapshot. That's what it looks like at time 2. That's a snapshot. That's what it looks like at time 3. That's all. So here's the important thing, though, right? Here is y versus x, because you're only looking at it at one particular time, right? And so this is the entire wave, right? Here nothing is going on. Here nothing is going on. So you're seeing the entire wave at one particular time. So it's y versus x. That's important. You'll see in a minute. Y versus x. Okay. Now, so these are snapshot plots of a transverse wave. So that's okay. So look, this is where you spray painted it. All right, that's where you spray painted it. So you can see all it's going to do is go up and down, up and down, up and down, right? But look at this is the disturbance. See how it's moving to the right? There it is at time equals 0, time equals 1 second, time equals 2 seconds, time equals 3 seconds, time equals 4 seconds. So it's kind of complicated, right? You know, the piece of the rope itself, right, that you sprayed just goes do-do-do-do-do. But what does the wave pulse do? The wave pulse, the disturbance, moves to the right. So these are snapshot, right? That's what it looked like at 0, 1, 2, 3, 4. Now, a couple things. Remember, it's y versus x. So what can you measure with a snapshot plot? Well, you can measure what's called the wavelength. So the wavelength is like from here to here. See, it's the same point, right? So it's coming down, bingo, coming down, bingo. So that's the wavelength. You could also say from here to here is the wavelength. You could also say from here to here is the wavelength. But a wavelength is meters, it's distance. So in order to be able to measure a wavelength, you have to have, this is the displacement, y, which is in meters, but you have to have a y versus x plot to measure wavelength. That's the important thing, okay? So for snapshot plots, y versus x, you can measure wavelength. That's it. You know, that's it. Oh gosh, this is tougher, huh? This is tougher. So this is a longitudinal wave, right? Okay. Now here, it's, you know, transverse is easy because what you see is what you get, kind of like, right? But with a longitudinal, we're going to say that this way is positive and this way is negative. Because remember, what's it doing? It's going like that, right? So it's positive and negative. Okay, so here's a displacement versus x. So here, the thing is moving this way. here, the thing moving this way, all right? But the pulse is moving 2 meters per second that way. But again, if you use spray paint to spray the spring, it's going like this, right? It's like the rope is going like this. Okay, maybe this will help. So think of this as a spring, and this is the spring at equilibrium, right? So we're just sitting there, you know. And then you put it, and then this is where the wave pulse. So this piece of the spring doesn't do anything, doesn't do anything, doesn't do anything. This thing moves a little bit to the right, or this way I should, that way. This one moves a lot that way. This one moves a little bit that way. This one doesn't move anyway. This one moves back. This one moves back a lot. This one moves back just a little, right? So it corresponds, right? Nothing, nothing, nothing. This one moves forward, positive X a little bit, right? A little bit. 4, a lot. 5, a little bit. 6, nothing. 7, negative, right? Going back, negative a little bit. 8, back a lot. 9, a little bit. 10, back to normal. 11, back to normal. So those are kind of hard. I mean, if you got to think about those, right? They're not so obvious. But that's what it looks like, okay? All right. But again, as soon as you see the displacement versus x, you know it's a snapshot, right? It's just what it looked like at one particular time. Okay, and now let's do the history. The history is the time dependence. But you're only looking at one particular part of the wave, right? So if it's a piece of rope, you know, you spray it with your spray can, and then you're just looking at what happens to that one particular piece of the rope over time. All right? That's what it means. All right, so these are harder, okay? These are harder, but whatever, you know. So history plot, the history of the location x1, so one particular place. That's all you're going to do. Okay, here we go. So these are snapshot graphs, right? Okay, so here you have this pulse moving to the right. This is T1, T2, so it's moving to the right, T3, T4. Okay, fine. Now, we want to look at this one particular spot, x1, okay? So all we're looking at is x1. So x1, 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 x1. One specific location, okay? Let's say this is okay, all right? So here, at time 1, x1 is right there. Right there. At time t2, x1 is up there. Up there. At time t3, x1 is down there. Down there. At time t4, x1 is on the right there. Okay? So look, it's completely different, right? It doesn't look like that, right? It looks like this sort of reversed almost. Okay? So all you're doing is you're plotting the history of one piece of the spring or one piece of the rope. All right? So this is a great slide because it really explains how to make a history plot. Okay, let's do another example. Okay, so here's all our, here's a bunch of snapshots again, right? We already talked about this. All right, all these snapshot graphs. Again, you see where you spray painted, down, and just up and down, up and down, up and down, and see the wave pulse moving to the right. Okay, great. Now what we want to do, we want to make a history graph. Okay, so what we want to do is we want to look at x equals 0. So that's where we sprayed it, all right? Okay, so x equals 0, all right? So at time equals 0, the spot is y equals 0, right? Bingo. Time equals 1 second, our spot is at negative whatever, right? Negative maximum, okay? So there it is. At time equals 1 second, it's right there. 2 seconds, it's back to 0. 2 seconds, back to 0. 3 seconds, maximum positive. 3 seconds, maximum positive. 4 seconds, back to 0. 4 seconds, back to 0. And so forth, okay? So this would be the history plot for this point, x equals 0. All right? History plot, the history of the rope's orange segment. Now notice, I've already said this, snapshots, y versus x, so we can get the wavelength. History, it's y versus t, right? History, t, right? And so what do you get for that? You can't get wavelength. Wavelength is in meters, you know. Here you have to get something in seconds, time. So you get what's called a period. So the period, we talked about this before. The period is a time for one orbit, one revolution, one cycle, you know, whatever you want to call it. So look, it's the time. So here, this is the same as this, right? You know, it's on the way down, right there, same as that. So this is the time it takes to go from here to the same place again. All right? Okay, so history graphs give you the period, because history means time. Period is time. Snapshots give you wavelength. So that's important. You got to remember that. All right. All right, now we want to talk about traveling waves. And we're going to make it simple. All we're going to talk about are sinusoidal waves, sines and cosines. What's so great about sines and cosines? Well, they repeat themselves, right? You know, sine, cosine, you know. So they have periods and they have wavelengths because they repeat themselves, right? So there's a nice sine wave. So we're going to say it travels to the right, or whatever, we don't care, you know. But this one travels to the right. Okay, so what we want to do, believe it or not, we want to figure out an equation. We want to figure out an equation for a traveling wave, traveling sine or cosine wave. And again, remember, there's two pieces to it. There's a piece of the rope that goes up and down like this, and then there's the disturbance that moves, whatever, to the right or to the left. All right? Okay, now remember, so snapshots, right? That's y versus x gives us wavelength. History, y versus t gives us period. Okay. Wow. Okay. That should just, I already said that. Okay, so here's a snapshot plot. And you know snapshot because it's y versus x, right? Which gives you a wavelength. And here's some more fancy words if you want. So this is called the crest. This is called the trough. I just call this the max. Call that the min, but whatever. But you should know this, the crest and the trough too. Just think of a pig trough, right? You know, crest of the wave. You know. Okay. All right. So now I want you to go back to when you took trigonometry, high school or whatever. You know. So this is what is the equation of this curve? Now remember, it's y versus x, so you can't have any time in it. And you know it's periodic in wavelength, so you better have a wavelength in it. So go back, you know, think back a long time. I don't know if it's a long time ago for you. It is for me, though. So this is the equation. And if you don't believe it, look in your trig book. All right, so y, which depends on x, right? The y's depend on x, equals a, that's the amplitude, cosine 2 pi x over lambda. So that's the equation. That's the equation. All right. Now, notice something. So again, there's no t because it's a snapshot. And again, it's periodic in wavelength, right? Because you know, that's a wavelength. That's a wavelength. That's a wavelength. Okay. Now let's just check this. Let's not believe it. Let's just check it. So we have y equals a cosine 2 pi x over lambda. Let's check in a few places, you know. Okay, let's put x equal to 0. So that means we have a cosine 0. We'll plug in your calculator. What's cosine of 0? 1. So we have a times 1 or a. Yep, works. Now let's try, let's put x. So this is a wavelength from here to here. Let's put x as a half a wavelength, all right? So let's do that. So x is a half a wavelength. So lambda over 2. Okay, so this 2 kills that 2. That lambda kills that lambda. Then we have cosine of pi, or cosine of 180. What's that? It's negative 1. So that would be minus a. Well, let's see. Is it? By golly, it is minus a. And you can plug in some more things. All I'm trying to say is it works. All right, so that's nice. Now, so that's the snapshot. let's do a history plot. And again, now it's y versus time, right? Yeah, I know I keep saying this. This is the y, this is the wave at one particular time. This is the wave at all time, right? Okay. All right. So what's the equation of that? Now this time you have period, you have time. So, I mean, you can either remember it from when you took trig or just kind of figure it out from this, right? Here you have x and lambda. Here you have t and period. What's it going to be? I mean, you can just look at it and guess, and you get it right. So here the equation is a cosine 2 pi t over period. Okay, let's try it. I don't know. If we put in 0, again, this is 0. Cosine 0 is 1. You get a. If you put half a period, you'd have a cosine 2 pi t over 2 divided by t. 2 is kill, period is kill. Cosine of pi is -1, so you get negative a. It works, all right? So both of those work. All right, now, wonderful. But come on, though, we want the wave to move, right? We want the wave to move to the right. So how are we going to do that? Well, I'll go back to high school algebra. So this is y equals x squared, right? This is y equals x minus 1 squared. If we had this one, it would be x minus 2 squared, and on and on and on, right? And so what are we doing? You know, we start off with y equals x squared, then we have y equals x minus 1 squared, and y equals x minus 2 squared. And what do we see? You know, here's a parabola, here's a parabola, here's a parabola. So, you know, the parabola's moving to the right. Agree? Parabola's moving to the right, you know? Okay, so just guess, all right? Just guess. How are we going to make our wave move to the right? So I'm going to skip some math. Sorry. And just give you the answer. But it should make sense from what we've just discussed, all right? So if we want our wave to move to the right, we're just going to say 2 pi x over lambda minus 2 pi t over t. Okay? So that's it. All right? So we're combining this and this, but then we're using what we learned with that. We want it to be x minus something, right? But we want it to continually move, right? Here, you know, it's only moving in steps of 1, right? X minus 0, x minus 1, x minus 2, da 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 da, you know? But we want it to move continually, so we're just going to have a time there. Okay? So that is the equation of a traveling sinusoidal wave. Woohoo! And this is going to the right. Remember, here, if it's a minus, it goes this way. If it were x plus 1, it'd be here, right? Because here, it's x minus 1, because if you put x equals 1, you get 1 minus 1, which is 0, so y is 0, you know? Okay, so this is minus if it moves to the right. If it were plus, it would move to the left. Okay, let's do an example. The displacement of a wave traveling in a negative x direction is y, depends on x and t, equals 0.15 centimeter cosine, blah, 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 blah. And you know it's moving to the negative direction because they have a plus here, all right? So x is in meters, t is in... So what's the wavelength? What are the wavelength, period, and frequency of this wave? So how do you do that? So there's a couple different ways. I'll show you the way I felt like when I did this, all right? I mean, there's different ways of doing it. Okay, so here you go. The general equation is this. So I'll just, right there, right? So let me multiply it out and make it easier. So the general equation is a cosine 2 pi x over lambda plus 2 pi t over t. And I put a plus because it's moving in the, to the left, right? Because that's what it says. It's moving to the left. Okay, now what we have, right, that's a general equation, and what we have yxt equals 0.15 centimeters cosine pi x over 2 plus t over 3, right? Okay, so let's do it. All right, I didn't ask for this on the question. What's the amplitude? So the amplitude is just the 0.15 centimeters, right? Okay, now this is really simple. This has to equal this, all right? So you just say 2 pi x over lambda equals pi x over 2. Now we want to find the wavelength. Okay, so again, there's different ways to do it. You could just algebraically solve for lambda, but I'm just going to do it a different way. I mean, it's the same, but whatever. It's equivalent. Okay, so this is 2 pi x. So let's multiply top and bottom by 2. That's not cheating, right? So put a 2 here, put a 2 here. That's totally legal. So now we have 2 pi x over 4. Well, 2 pi x, lambda 4. What's lambda? 4, right? So lambda is 4 meters. Okay, you didn't have to do that. You didn't have to multiply by top and bottom by 2. You could have just solved for lambda, but it's easier that way. All right, let's do the other one. Okay, let's see. This has to be the same as this, right? Yeah. So we just say 2 pi t over period equals t over 3. Okay, let's just do the same little trick we did before. Let's multiply this by 2 pi over 2 pi. So now we have 2 pi little t over 6 pi. Well, that equals that. So that has to equal that. So the period is 6 pi. So this would be meters. This is in seconds. Okay, then frequency is 1 over the period. So it's 1 over 6 pi seconds to negative 1 power. We can say 1 over 6 pi hertz, right? Because a hertz is an inverse second. So there you go. So that's what I mean. This is really nice, you know. This is really nice because you can easily pick off the lambda and the period without doing a whole lot of work. All right, let's quit.